Last time we built the momentum equation the hard way, Newton's second law, force by force, on a moving parcel. But there's a deeper pattern underneath. One single bookkeeping rule generates the equation for mass, for momentum, and for energy. Derive it once, and the rest is just filling in a blank. Here's the idea. Fix a box in space, a control volume, and watch some conserved quantity inside it. Pick anything with a density, mass per volume, momentum per volume, energy per volume. Call that density phi. Now the amount of phi inside can only change for two reasons. Either phi flows across the walls, in or out, or it's created or destroyed inside by a source. There's no third option. So the rate of change inside equals the net flow in plus the sources. That sentence is the whole of conservation. Let's turn it into math. Take the box, a tiny cube. The amount of stuff inside is phi times its volume, so its rate of change is the time derivative of phi times the volume. Now the flux, call it F, is how much phi crosses a unit area each second. Look along X. The left face lets flux in, the right face, a small distance away, lets a slightly different flux out. The net outflow along X is the difference between the two faces times the face area, which works out to the rate of change of the flux in X times the volume. Add the same for the other two directions, and the total net outflow is the divergence of F times the volume. Conservation says, rate of change inside equals what flows in, which is minus the outflow plus the sources. Divide through by the volume, and everything collapses to one line. The time derivative of phi plus the divergence of its flux equals the source. That's the master equation. Look at what we've got. Partial phi partial t plus div f equals S3 slots, a density, a flux, and a source. Every conservation law in fluid dynamics is this one template. You just decide what you're conserving and fill in the three boxes. Let's fill them. First, conserve mass. The density phi is just the mass density, rho. The flux, how much mass crosses a face each second, is rho times velocity, the mass carried along by the flow. And the source, mass isn't created or destroyed, so it's zero. Drop those three into the template. Partial rho partial t plus the divergence of rho u equals 0. That's the continuity equation, and it says exactly what you'd expect. Mass piles up inside the box only as fast as it flows in. Now a special case worth its own line. If the fluid is incompressible, density constant, like water, then rho comes out of both terms and cancels. What's left is beautifully simple. The divergence of velocity is 0. Physically, whatever volume flows into the box must flow right back out. No squeezing, no expansion. A divergence-free velocity field. That single constraint is what makes incompressible flow its own world. Now the payoff. Keep the same template, change only what we're conserving. This time momentum. The density is momentum per volume, rho u, now a vector, because momentum has direction. Its flux is rho u, carried along by u itself, the outer product momentum transporting by the flow. And the source, forces, exactly the ones we found last time, the pressure gradient, the viscous term, and gravity. Fill the slots, and out comes the momentum equation. Partial rho u partial t plus the divergence of rho uu equals minus grad p plus mu del squared u plus rho g, same machine, different quantity. And it doesn't stop. Conserve energy instead. The density is energy per volume, the flux is energy carried by the flow, and the source is heat added plus work done. Same template, third equation, the energy equation. Mass, momentum, energy, one rule 3 times. But wait, we derived the momentum equation last time too, and it looked different. It read rho times the material derivative. That version followed a moving parcel. This one watches a fixed box. Same physics, 2 viewpoints, and the two are the conservative and non-conservative forms. They're connected, exactly, by the continuity equation we just derived. Converting between them is its own story, and that's where we'll go next. So here's the whole picture on one slide. One conservation template, three quantities, mass, momentum, energy, two viewpoints, the fixed box and the moving parcel. Master this single line, and every governing equation of fluid dynamics is just a blank you fill in. Next time, how to convert one form into another. Tell me what you want to see in the comments.